Well, hello. Let's go ahead and move on to hexadecimal number system, base 16. All right. So just as to show you that nothing new here. Okay. Base 10, 10 digits, first digit starting with 0. Okay. Hexadecimal, same thing, but we have base 16, 16 digits, also starting with 0. Oh, wait a minute. There's 10 digits, 0 through 9. Hey, we need 6 more digits. Well, let's see. Could I use hashtag, exclamation mark, question mark? Well, I probably wouldn't remember those. So let's come up with 6 more digits that we can easily remember. Oh, the alphabet kind of helps us out there. There's a sequence of symbols that we can easily remember. A, B, C, D, E, and F. All right, so decimal to base 16. Let's take a look at this. And I've got some spaces here. So showing the in decimal space there, just for readability. But here is the decimal value, decimal from 0 to 15, 16 possibilities. Hexadecimal, 16 possibilities, 0 through F. So each one of these is equivalent. 0 decimal, 0 hexadecimal, 1 decimal, 1 hexadecimal. And we can keep on going, 2 decimal, 2 hexadecimal, all the way to here, 9 decimal, 9 hexadecimal. What about 10 decimal? Okay, well, and remember, in decimal, we only had 0 values, or 0. We had 10 digits we could use, 0 through 9. In hex, we still have some more digits we can use. So 10 decimals equal to A hexadecimal, 11 decimal, B hex, 12 decimal, C hex, 13 decimal, D hex, 14 decimal, E hex, and 15 decimal, F hex. This will make more sense in just a moment. So first of all, why are we using hexadecimal? In my world of networking, we use it in 2 places. We see it very common in Ethernet MAC addresses displayed in hexadecimal. And in another world of mine, the world of IPv6, still part of networking, of course, we use hexadecimal numbers to represent IPv6 addresses. And it's actually an easier way to go. So let's take a look here. If I have 4 binary, using 4 bits to represent binary values, 1s, 2s, 4s, 8s, there's my columns. Here's every combination of 4 bits, from 4 zeros to 4 ones. This is every possibility. So how many possibilities are there? There's 16. This is why we use base 16. Okay. In decimal, we saw it 0 through 15, 16 possibilities. But let's look at in hex. So in hex, I have 0 through F. This is every possible combination of hexadecimal values, using one digit from 0 to F. Okay. So if converting from hex to binary or binary to hex, we can see that any combination, this is the key thing, any combination of 4 bits can be represented by a single hexadecimal digit. And let me say that again. Any combination of 4 bits can be represented by a single hexadecimal digit. It's a lot easier to look at the hexadecimal value than the binary value of the data. Okay, instead of 1011, it's easier just to see a B. All right, so this will make more sense as we do some conversions. Let's convert from hexadecimal to decimal. Okay, so here's every combination. Once again, shows all the equivalency. All right, so in hexadecimal, we said we had 0 through F. Okay, those are the 16 digits that we can use. Okay, decimal 0 through 15. So let's kind of use this as our between hexadecimal and decimal. Okay, so in hexadecimal, the first column is the column of ones. Okay, just like our other integer-based number systems. Base 10, base 2, the first column, the column of ones. The next column, hexadecimal, base 16. What's the next column? Let's see, in base 10, it would be 10 times this. In base 2, it would be 2 times this. Oh, I know, in base 16, it'd be 16 times this, 16. We'll stop there. Don't worry, we're not going to go any further. All right, let's convert these to decimal. 8 in decimal is the same as 8 hexadecimal. 9 decimal is the same as 9 hexadecimal. Now, if somebody was 9 years old and they just had a birthday, we could say happy 9th birthday in decimal. Okay. If they turn 10, we could say, hey, happy 10th birthday. You're 10 years old in decimal. But you know what? You're A years old in hexadecimal, base 16. How old would they be if the following year? Well, if they're 11 years old decimal, they'd be B years old in hexadecimal. What I'm trying to say is those are the same value, they are equivalent. If you're 14 years old, you are E years old in hex. If you're 15 years old in decimal, you're F years old in hex. Oh, what happens when they turn 16? Well, remember, same thing as our base 10, base 2 number systems. We are at the end of the values, the digits, the symbols in this number system. F is the last value. What did we do in base 10? What did we do in base 2? We started over. We put a 0 here and increased the next column by 1. So 16 decimal would be the equivalent to 10 hexadecimal, base 16. That's important. That's not 10 decimal. That's not 10 binary. This is 10 base 16. And by the way, I'll show you later how we represent these. Would be with a little subscript here, 16 here. We could put a little subscript here, 10 here if we wanted to make it more clear. Okay, how about 17? Just add 1 here. We got another digit to go from 0 to 1. Okay, and you might be seeing, we're going to show this in a moment. Oh, yeah, this is 116 and 0 ones. Hey, this is 116 and 1 1, 17. Pattern to this. It's the beauty of math. It's the beauty of number systems. Consistency. Same rules apply. It doesn't matter. No exceptions here. Okay, well, here we are. Follow along for those students of mine in your homework, number 11 here. Okay, what if I had this hexadecimal value? Now, 0 16, ignore it, right? 6 ones. Well, that's 0 16, 0 times 16. We don't have to worry about that. 6 ones, 6 times 1, 6 ones, or 6. Yeah, that easy. Okay. How about 0A hexadecimal? Okay, again, 0 16s. But A1s, okay? A1, what is A? That's 10, okay, in decimal. Okay, 10 times 1 or 10. Okay, 0A or just A in hex is equivalent to 10 in decimal. Okay, how about 13, 1 3 in base 16 hexadecimal? Well, in this case, we have 116, 1 times 16, and 3 ones. 3 times 1. 16 plus 3, 16 ones plus 3. Well, let me say that again. 116, not 16 ones. 116 plus 3 ones equals 19. Are you getting this a little bit? Just got to remember what number system we're dealing with. Same rules. All right, let's do another one. What if I had A0 base 16? How many 16s do I have? Let's see. Oh, it looks like I have 10 16s. How many ones do I have? 0. Well, what's 10 16s plus 0 ones? 10 16s is 160 plus 0 ones. Hey, 160. Not too bad. Okay, how about BC? Uh-oh. Now I got to do some multiplication. It's not that hard though. B is in the 16 column. C is in the ones column. So let's look at this. B, where's B? Is 11. So I have 11 16ths. 11 times 16. That's 176. How many ones do I have? Let's find that. C is equivalent to 12 in decimal. So let's do 12 ones, which is 12. The 176 plus 12, 188. Okay. Don't let it throw you off. Just look at step by step. How many ones? How many 16ths? Okay. This is a true story. So my mom, many years ago, when she was with us, right? So she had a birthday. And I got her a happy birthday, happy 50th birthday mom card. And my mom looks at the card. She goes, Rick, I haven't been 50 in a few years. I said, Mom, this is base 16. Okay. She didn't quite get the joke. But my brother, the physicist, got the joke. My brother, the nurse, I had to explain it to him. But my brother, the physicist, thought it was funny. Okay. But none of this, you don't have to have a degree in physics to understand this. We all, it's not that hard. Okay. If you count in decimal, you can understand any number system. Let's look. How old was my mom in decimal? She was 50 in base 16. So what is that? What do you think it is? How old was my mom? Yeah, I think you got it. How many 16s do we have? We have 5 16s and 0 ones. Well, 5 times 16 is 80. 0 ones is 0. 80 plus zeros. Oh, I got 180 there. Oh, I did. She wasn't that old. Okay. Oh, my goodness. Let me change that. There we go. I have no problem with making mistakes in my videos sometimes and just leaving them in there. All right. Show you how I correct them. And you can catch my mistakes. That's always a good thing too. My students are great at catching Rick's mistakes. And I make a few of them. We all do, right? All right. Especially in my PowerPoints, copy and paste too much. All right. So back to this. My mom is 80 decimal, but 50 in hexadecimal. So here's the thing. When you get older, you don't have to worry about getting older. Just change number systems. That's all you got to do, right? Okay. Let's go from decimal to hexadecimal. Okay. All right. Again, in hex, we have the number of ones, number of 16ths, and let's do a decimal value here. Again, 9 in decimal is 9 in hex, 10 decimal, A hex, 12 decimal, C hex, 15 decimal, F hex. Okay. Let's look at number 17 here, 9 decimal. I think we can figure that out. Okay, 9. What if I owed you $9? Okay. Now let's use our little money system again. I can give you $1 bills or $16 bills. Okay, and I can give you 0 to 15 of each. 0 to 15 of each. 16 total numbers I have. 0 to 15 of each. 0 to 15 of each. Well, I'm not going to give you any $16 bills. But how many $1 bills I can give you? I can give you 9 $1 bills. Again, we're talking hexadecimal here. 9 $1 bills. Now I don't owe you any money. How about if I owed you $10 in decimal? What would I pay you in hex? Well, I'm not going to give you any hex. I'm not going to give you any $16 bills, but I can give you we're using hexadecimal values here, $1 bills, which is equivalent to 10. Okay. How about 21? Okay. If I owed you $21, am I going to give you any $16 bills? Yes, I can give you 2 of those. I'm sorry, 2. 1 of those. 2 would be 32. Okay. I can give you 1 of these $16 bill. So I owed you 21. I just paid you one $16 bill. So what do I owe you? Just paid you that. I'm going to subtract that from the 21 I owe you, $16. 16 minus from 21, $5. So I owe you $5 left. How many ones am I going to give you? 5 $1 bills. 5 times 1 is 5. I don't owe you anything. Another way you can look at this, 1 times 16 plus 5 times 1, 5. 16 plus 5 is 21. Let's look at another one. 33. Okay. If I owed you $33. Now this time I'll give you two $16 bills. Okay. I just paid you $32. I gave you two $16 bills. Now what do I owe you? $1. So I'm just giving you, what do I have left over? I'll just give you one $1 bill. Now I owe you nothing. Again, 2 times 16 is 32 plus 1, 32 plus 1 is 33. Okay, how about 50? What's the equivalency here? How many 16s am I going to give you? How many 16s? If I look at that, how many 16s? 1, maybe more, 2? How about 3? Yeah, 3 16s is 48. Now what do I owe you? $2. I give you two $1 bills. There we go. Now I owe you nothing. 3 times 16 is 48. Plus 2 times 1, 2. 48 plus 2 is 50. Here's something else you can do. You know somebody turning 50 years old? Okay. You can wish them happy 32nd birthday in base 16. It's the equivalency. Again, you know, if people, some people are worried about getting a little older, just change number systems. Okay, what's 160? I think we're getting the hang of this. How many 16s am I going to give you? How many 16s can I give you? Okay. Let's put in, how about an A here? A is 10. By the way, uppercase or lowercase, I didn't fail to mention this. Doesn't matter. Okay. They're both the same. You'll see it expressed in both ways in the world of networking, computer science, etc. All right. A, that's 10 16s. That's 160. Oh, great. We're done. Well, not quite. Let's not forget our 0 here. Okay. To make sure we position this A under the 16 column. 10 116. 10 16s, not 10 ones. Okay. So 10 16 plus 0 ones. 160 plus 0 is 160. 170. How about A? I used lowercase here, didn't I? 10 16s. Okay, that's 160. What do I have left over? Oh, I have 10 left over. Hey, how about an A here? That'll work. 10 16s plus 10 ones. 160 plus 10 is 170. 171. Let's kind of do this similar. 171, we had 10. So again, 10 16s, A 16s. 171 minus the 160. Now we have 11 left over. What's 11? 11 decimal. That's what we have left over. Oh, there we go. Right there. See that B? That's the equivalent to 11. Okay. So we have 10 16s plus 11 ones. 160 plus 11 is 171. Again, if you're a student of mine where we had the numbers previously and coming up, that's where you make sure you put it in your assignment. That's part of our assignment. Have you turn in. Okay. All right. Let's go from hex to binary. This is actually not too bad. It's actually very easy. Now that we understand this chart, hopefully, let's make sure we understand it. Why do we use hexadecimal? Again, because binary, representing any 4 bits from 4 zeros to 4 ones, can be represented by a single hexadecimal value. Okay. These are all the hexadecimal values or digits from 0 to F, base 16. Okay, 4 zeros to 4 ones. Okay. Matter of fact, you can add this up. Okay, how did we get 10 decimal? Okay, well, we have 1 in the tens place, 0 in the ones. Okay, that's a hex. Binary 1 8 plus 1 2 is 10. Let's go way down here. 15 decimal, F hex. 1 8 plus 1, 4, plus 1, 2, plus 1, 1, 8 plus 8 plus 4 plus 2 plus 1, all ones here, is 15. All right, so what happens when I see a value like this? So you will see many times, we'll talk about this when we get into IPv6 and other things, but also Wireshark. Wireshark likes to show us things in 8-bit bytes or octets, okay? 8 bits. So when we see 8 bits or a string of bits, it doesn't matter, but here I'm showing you 8 bits. It's a lot easier to represent this in hexadecimal, and it's actually very easy to do because all we have to do is take these 4 bits, just divide it in half, 1100, and find its equivalency. 1100 is right here, it's a C. Then look at this next 4 bits, completely separate, 4 zeros. Okay, 4 zeros is a 0. Now, you could work this out in mathematically as well. 8 plus 4 is 12. Well, 0C, C is 12. Okay, all right, or 0 16s and 12 ones. But really what I want you to see is this. All you need to do is capture each 4 bits and find the binary representation of it. That's the most important part here. Okay. How about this? Again, when we see these 8 bits, how can we represent it in hex? Just capture each 4 bits separately. 1000. 1000 is an 8 in hex. How about over here? 1101 is actually D in hex. Let's find that. 1101 is a D in hex. Now, by the way, this works out mathematically as well. Okay, let me show you. Okay, if I made this one long binary value, I could add, and this is going beyond. Okay, this again, what I want my students right now to get is that we can take any 4 bits and just represent it as a single hexadecimal value all by itself. But just to show those of you that are thinking, does this work out mathematically? What if this was an 8-bit number? Does it still equate to this? Yes, it does. 18, I'm sorry, let's make this instead of 8421, let's make it one long 8-bit value. So let's make this a 128, 64, 32, 16, 8421. 128 plus 64 plus 16 plus 8 is 216. And hex, D, which is 13 16s, plus 8 ones is 216. It works out mathematically as well. Okay, if you get that, great. If you don't worry about it right now if you're one of my students. But there's no changes in how we learned things before, converting between binary and decimal. It's all still equivalent. All right, so I think that does it. I hope this helps you understand a little bit about number systems. I had one little video here about, now that you know this, how can you impress your friends? I'll do that next.